Hey, welcome. This video is on polynomial equations. It's kind of a long section, so be ready. Here we go. So we're going to try to solve equations like this example, 2x to the third plus 14x squared minus 11x plus 12 equals 0. We'd like to think about how many solutions are there. Here's some examples of some equations. X plus 7 equals 0. You can see that the answer to that equation is negative 7, right? There's one solution. In the second row, x squared minus 2x minus 8 equals 0. We could solve that by factoring and setting each factor equal to 0, or by using the quadratic formula, but there's two answers. The third row is a degree 3 polynomial. First one was degree 1, second row is degree 2, third row is degree 3. So we're going to solve this one today. And kind of trust me here, these are the three answers. Negative 2, positive 1, and positive 2. There's three answers. Actually, we could do that one by grouping. We could factor in x squared from the first pair and a negative 4 from the second pair. So we already have the tools to solve that problem. The fourth row, x to the fourth minus 16, that actually has four solutions. We could factor it using the difference of two squares, and then setting each factor equal to 0. We could use the square root property to solve at that point. So that one has four solutions. So notice that the number of solutions depends on the exponent of the variable. If it's a 1, we got one solution. 2, two solutions. 3, three solutions. 4, four solutions. Except this last row. That one only has one solution. And let's look at that one a little bit more closely. The solution 5 is actually a solution twice. So let's look at that trinomial. That factors to x minus 5 times x minus 5. Right? You could verify that. So each factor, if we set each factor equal to 0, we get an answer of 5. So there's only one solution, x equals 5, but what we say is it's the solution of 5 with a multiplicity of 2. So that means it was a solution twice. So then we have this rule about the number of solutions of an equation. A polynomial of degree n has n solutions, where any solution of multiplicity p is counted p times. So that just means we could have an answer that appears twice. So it's counted twice. Or it could be a solution 3 times. So it's counted 3 times. But there are n solutions. So if the polynomial is degree 5, that means there could be 5 solutions. There could be 5 different solutions. Or they could all be the same solution. Or we could have one solution twice and another one 3 times. But there could be as many as 5 solutions if the degree is 5. So if we look at this equation, x minus 5 squared times x plus 2 cubed, if we multiply that all out, that's a 5th degree equation. Anyways, x minus 5 squared means x minus 5 times x minus 5. X plus 2 cubed means there's 3x plus 2's. So we have two answers. We have negative 2 and 5. But the solution of negative 2 has a multiplicity of 3, and the 5 has a multiplicity of 2. So negative 2 is an answer 3 times, and 5 is an answer twice. Okay, so now we're going to talk about finding rational solutions. This is a very complicated topic, and I want you to really know, what is expected from you from your teacher. There's different ways of approaching this. And what I'm thinking about is a calculator. Some teachers are very anti-calculator. They want you to follow all the rules without a calculator. Or they may give you an exam and you cannot use a calculator. In my class, I'll let you use a calculator, so I'll kind of talk about the rules I have you do. But if you're not in my class, you really want to know, what are the techniques you have to show, and how much of a calculator how many things can you do on a calculator without showing your work? That's really the big thing. Okay, so in the last video that we did, what we did is we said, okay, here's one factor that's given, and then I want you to complete the factorization. Now in this section, they're not going to give us any factors. So there's going to be a lot of trial and error, but we also have some rules, some theorems and properties that make it a little bit easier. Okay, so here's our first theorem that gives us a set of potential rational solutions. This is called the rational root theorem, and I know this notation gets a little complicated. So here's our polynomial equation. Just keep note that it's written in descending order from x to the n to the constant, and a sub 0, a1, a2, all the way to an, they're just numbers. Okay. And we're going to talk about this fraction, c over d, and it's always reduced. And it could be a solution to the equation. If it is, c is a factor of the constant, so we're going to use c for constant, and d is a factor of the leading coefficient. Okay, so just remember, c is constant, and d is the leading coefficient. So that's the number that's in front of the first term, in front of the very first variable. Okay, I know that was confusing, so let's look at an example. 2x to the fourth minus 11x cubed plus 14x squared minus 11x plus 12 equals 0. We're not going to solve it. We just want to know the possible answers. Not the answers, the possible answers. So another name for the answers is solutions. Another name is roots, R-O-O-T-S, roots. Another one is zeros. Zeros because it's where it hits the x-axis on a graph. Okay, so let's start with C and D. C is the constant, which is 12, and D is the leading coefficient, which is 2. So what we want to do is write down all the factors of 12 and all the factors of 2. Well, the factors of 12, anything that goes into 12, positive and negative. So 1 goes into 12, 2 goes into 12, 3, 4, 6, 6 and 12. And for 2, it's just 1 and 2. Okay, so C is the constant, and we just wrote all the numbers that go into 12. And I try to put them in order. You don't always have to put things in order, but it makes it so much easier when you do. Okay, so now what we're going to do is we're going to make a list for C over D. So D is in the denominator. So all those numbers, 1, 2, 3, 4, 6, and 12, you're going to put them all over 1 at 1 at a time. So if you put 1 over 1, what do you get? 1. 2 over 1, 2. 3 over 1, 3. So it's the same numbers. Now when you put them over 2, 1 over 2, and then 2 over 2, well, 2 over 2 reduces to 1, so we're not going to list that again. Then 3 over 2, and then 4 over 2, which is 2, so we're not going to list that again. 6 over 2, which is 3, we're not going to list that. 12 over 2, which is 6. Okay, so there's our possible answers. Let's kind of go through that again. So take the top row and put them all over 1. 1 over 1, that's the first answer, 1. 2 over 1, that's 2. So we're putting them all over, let me just circle this, let's see. So we're starting with this 1 right here, and we're putting everything over 1. So 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, and 12 over 1. Now we're moving on to the 2. So then we put the first number, well, 1 over 2, so that's this one, 1 over 2. And then what's 2 over 2? Well, that reduces to 1, so that's why we're not going to list it. If you write it, you could write plus and minus 2 over 2, but that equals 1, so that's why we don't write it down. The next one would be 3 over 2. That's right here. After that, it would be 4 over 2. Well, what's 4 over 2? That's equal to 2. So we already have that on the list, so that's why we cross it out. What's next? 6 over 2. Do we already have 6 over 2? Yeah, we do, right? That's 3. So that one's gone. What's next? 12 over 2. That's equal to 6. Already on the list, so we don't need it. So that is our complete list that we have in the box. Now, notice that, sorry, I kind of wrote on some of this stuff here. Let me erase it. Notice the number of possible solutions that exist. How many numbers are on that list? Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8. But there's a plus and a minus. That means there's 16 possible solutions. There are 16 numbers there. How many solutions could we have to this equation? Well, look at the degree of the polynomial. The original polynomial is 4. So since the degree of the polynomial is 4, only 4 out of that 16 is going to work. So that means 12 of those numbers are not going to work, at least 12. Remember that one of those 4 could appear twice. So for example, our answers could be -1, -2, 3, and 4. Or it could be -1, -2, 3, and 3 again. Probably not, but it could, something like that. That's what could happen. An answer could appear twice for one of our 4 solutions. All right, let's do the same thing. I know it's a little complicated. Again, we're not solving this. We're just kind of talking about what are the possible solutions, because we're not given anything to start with. Okay, this is called the rational root theorem. All right, so let's write down our C and D. C is 8 and D is 3. So write down all the factors of C, which is plus or minus 1, 2, 4, and 8. That's our constant. And then D, since D is 3, the factors of 3. 1 and 3. So now let's list C over D. So we're doing the same thing we did last time. 1 over 1, 2 over 1, 4 over 1, 8 over 1. Then we move on to the 3, 1 over 3, 2 over 3, 4 over 3, and 8 over 3. None of these are repeats, or none of them reduce, I should say. So that's why we get all those possibilities. So plus and minus 1, 2, 4, 8, 1/3, 2/3, 4/3, 8/3. Sometimes when we do the synthetic division, oh, I didn't tell you what we're going to do. We're going to have to find some of these by synthetic division, and sometimes you have to use fractions, but you know how to do that. All right, now we're actually going to solve it. Let's do our C over D. Our D is 1, and our C is 24, so that gives us 1, 2, 3, 4, 6, 8, 12, and 24. Writing our list of C over D, well, anything over 1 is the same numbers. So it's really nice when the leading coefficient is 1, when there isn't a number in front of the highest degree variable. X to the third is all by itself. That's great. All right, so we have a degree 3 polynomial. What we need to do is we need to find one solution. Now this is when I was talking about calculators. If your instructor is okay with it, then you use your calculator. I like to use the Casio FX991EX at this point. This is 2021, so who knows in 2022 what calculators will be available. But it's a real nice, easy calculator to use. I have videos on how to use the calculator, how to solve these equations. So your calculator will solve this. Okay. Now what I do in my class is I let you use your calculator, but you're not supposed to show me that you're using your calculator. Okay? So if you use your calculator, use the polynomial feature, plug it in, and it'll solve it for you, and it'll actually give you the three answers. It'll give you what each one is. So you could do that if your teacher allows you to. If your teacher doesn't allow you to, well then you go from this list. So what I would probably do is I'd probably start with positive 1. That's the easiest one, right? And I would do my synthetic division. And notice in red here, I have a remainder of 12. What does that mean? It means that 1 isn't a solution. We have to keep going until we get a 0. Okay, so what else should you try after 1? Maybe negative 1? Let's try negative 1. I got a remainder of 30. No, it doesn't work. All right, let's keep going. What would you want to try next? How about 2? Yeah, that one works because we got a remainder of 0. Okay, so if you're able to use your calculator, and 2 would be one of the solutions. That just helps you decide. Don't waste time doing this synthetic division with 1 and negative 1. Go right to 2. But if you're not able to use a calculator, then you start trial and error until you get a 0 for a remainder. Now there's a couple other rules that will help us with determining what numbers to try, but they're not great rules. It's still a lot of work, so don't think it's not a lot of work, because it is. Or you might be thinking, gosh, there's got to be easier ways. No, not really. All right, so 2's our answer, so keep that in mind. So now the answer that we got, that quotient, 1, negative 1, negative 12, let's put that in variable form. And we could solve that equation now. Either it factors. If it doesn't factor, then we have to use the quadratic formula. I think that one factors, right? x minus 4 times x plus 3. Yeah, the factors of 12 are 1 and 12, 2 and 6, and 3 and 4. 3 and 4 will give you a -1. So we have two answers, +4 and -3. Actually, do we only have two answers? No, there's three answers, the 2. So don't forget the 2 that we found earlier. So those are our three answers, -3, 2, and 4. You should try to put them in order from lowest to highest. That's it. Let's do another one. Okay, here's another polynomial of degree 3. Let's do our C over D. This is called the rational root theorem. So we did this one earlier. ±1, 2, 4, and 8, and then 1/3, 2/3, 4/3, and 8/3. So that's the rational root theorem. Now the factor theorem. The factor theorem is we need to show that we're going to get a 0, and we want to use synthetic division. So we're going to try -2. Again, why negative? Why did I start with -2? Because I used my calculator to see which one would be the easiest. Okay, so if I didn't have a calculator, I would start with 1 and then -1. Those won't work. Then I would try 2, then -2. Then I'd finally get to the -2. And it is quite possible that all the answers are fractions. So that happens sometimes. All right, so do the work with -2. Pause the video and make sure you got that to work out. Okay, now we're going to factor that answer that we have. So write it in variable form first, 3x squared minus 13x plus 4. And that does factor to 3x minus 1 times x minus 4. You may want to do the grouping. Again, pause the video, make sure your factoring is okay. 3 times 4 is 12. There's 1 and 12, 2 and 6, and 3 and 4. 1 and 12 would be the pair to use, both negatives. Anyways, I didn't show all the work because it's kind of a lot to show on here. So set each of those equal to 0, so you get two answers. 1/3 and 4. Yeah, forgive me if I skip some steps here and there. Hopefully you're okay. Remember, there's always tutor centers. You can make appointments with a tutor or go over things if you get lost. Okay, so are those our two answers? Oh no, we have one more, right? Don't forget the -2. Okay, before we do our next example, I put a little note here. Once one solution is found in a third-degree polynomial, a trinomial is left to be factored to obtain the last two solutions. If it cannot be factored, then the quadratic formula must be used. Actually, it's not exactly true. If there's only two terms, you could use the square root property, but you could always use the quadratic formula. Okay, here's our example 5, x to the third minus 3x squared plus 2. Looks kind of simple, right? A little short. Let's do our C over D. Our C is 2, so that's only plus and minus 1 and plus and minus 2, and our D is 1. So everything over 1, which is the same numbers as C, right? Plus and minus 1 and plus and minus 2. All right, let's do our synthetic division. There's no x term, so make sure you put a 0 for the x term. So when you write your numbers inside the division box, it'll be 1, -3, 0, and 2. And then try, start with 1, then -1. There's only 4 numbers that are possible here, so hopefully one of those 4 work at least. So let's try 1. Hey, it works, right? Yeah, pause the video. Make sure you could show that if you use C as 1, we get a remainder of 0. So that means 1 is a solution. Now we'll write that in variable form. Can that factor? X squared minus 2x minus 2. 2 times 1 is 2. It doesn't factor. What do we do? Right, quadratic formula. So A is 1, B is -2, and C is -2. Maybe it's been a while. So we plug all those numbers into the formula. So inside we get 4 plus 8, which is 12. 2 plus or minus square root 12 over 2. Simplify square root 12, which is 2 square root 3. And then we can reduce it as long as there's a number that goes into all 3 numbers at the same time, which is 2. So our final answer is 1 plus and minus the square root of 3. So that's actually 2 answers right there. 1 plus square root 3 and 1 minus square root 3. And then don't forget about the 1, right? So 1 plus square root 3, 1 minus square root 3. Anytime you have radicals or square roots, they're always going to come in pairs. There's always going to be a plus and minus. All right, here's another one. Again, before we do this one, just a little note. We could have complex solutions. And again, with complex solutions, they always come in pairs. How do we get complex solutions? By using the quadratic formula or the square root property. In either case, there's always that plus and minus in front of the radical. That's why they occur in pairs. All right, let's do it. So let's do our C over D first. C is plus and minus 1, 3, and 9. And D is plus and minus 1 and plus and minus 2. So everything over 1 and then everything over 2. So there's our list. We got 12 numbers. All right, so let's start our synthetic division. Try 1, -1, 3, -3. If those don't work, probably 9, then -9, but that's unlikely. Probably the 1/2 and the -1/2. I know, pain in the butt, right? Shoot, so you tried your work and we had to resort to using 1/2. So 1 didn't work, -1 didn't work, 3 doesn't work, -3 doesn't work, 9 doesn't work, -9 doesn't work. So you try 1/2, there you go, it works. Okay, so now write it in variable form. There's no x term, so we have to put a 0, so it's 2x squared plus 18 equals 0. Subtract 18 on both sides. We're going to use the square root property, then divide by 2. X squared equals -9. Take the square root of both sides. So x equals plus and minus the square root of -9. Now, if the directions only said real solutions, then these will not be solutions. But if it doesn't say anything, then they're asking for any complex solutions as well. So they're just asking for anything. So square root of negative 9, you put the I in front and you keep the 9 inside. Square root of 9 is 3, so plus and minus 3i. Okay, so there's two answers, and then the 1/2 is the third. So those are our three answers. 1/2, positive 3i, and negative 3i. Okay, we're going to talk about Descartes' rule of signs. Rene Descartes, philosopher, mathematician, writer. You might have heard about Rene Descartes. French, I believe, French, but lived where the Netherlands are. Dutch. Anyways, he's known for the Cartesian coordinate system. Here we're going to talk about Descartes' rule of signs. But he was also a famous philosopher. He's probably known for that phrase, I think, therefore I am. You can look him up, it's all online. Okay, so what we're going to do is we're going to talk about his rule of signs. So this is 1600s, 1620s, 1630s. We're talking about the number of solutions for an equation. So we know how many there are. What we would like to know is, what are they like? Are they positive? Are they negative? And that's what this rule does. It's going to give us the number of positive roots or the number of negative roots. Kind of. Okay, let's read what this says. The number of positive roots is either equal to the number of variations in sign of p of x or less than that by an even number. That's where this rule gets vague. It's equal to the number of variations. So what does that mean? That means does it have a different sign from the term before it? Does it vary from term to term in sign? That's what we mean by variations in sign. And then we'll talk about or less than that by an even number. The number of negative solutions is either equal to the number of variations in sign of p of negative x or less than that by an even number. I know it's not the greatest rule. It's just something we have to talk about. So what does less than that mean? Well, we were talking about complex solutions. They occur in pairs because of that plus and minus that's in front of the radical in the quadratic formula. So if let's say we get 3 positive solutions. Well, 2 of those could be complex, and we don't know. So if we get 3, then we have to subtract by 1. It could be 3 or 1. If we get 5, it could be 5 or 3 or 1, because we keep subtracting by 2. Because again, this rule doesn't tell us if they're complex. They could be complex, and if they are complex, they come in pairs. If we get 4, we got to subtract by 2. It could be 4 positives. It could also be 2 positives or none. Because if we start with 4 and we subtract by 2, 4 or 2 or 0. If we get 5, 5 or 3 or 1. If we get 6, 6 or 4 or 2 or 0. How about 7? 7 or 5 or 3 or 1. You can never have a negative number of solutions. So we either stop at 0 or 1. So here's some examples. If you get 2 changes for p of x, it's 2 or 0. 3 or 1. 4 or 2 or 0. 5 or 3 or 1. 1, then it's just 1 because we can't subtract 2 from 1. Okay, that's for p of x. Now, p of negative x, what that means is we replace x with negative x and then simplify it. And then we're going to count the sign changes. All right, let's do an example. What the heck is this, right? So we're not going to solve. We're just going to use this rule of signs. Okay, so we were talking about a polynomial, so let's just change it to p of x. You don't really have to, but I'm going to do it just to be proper. Okay, so what we're going to want to know is, are there any variations in sign in this polynomial? Is the sign of any term different from the sign of the previous term? So we'll look at the second term. Is it different? No, the first one's positive, the second one's positive. Look at the third term, the 11x. Does it have a different sign from the second term? No. Again, another positive. Look at the fourth term, the 6. Is it different from the third term? Is it different from the previous term, the sign? No. This means there are no variations in sign, so there are no positive solutions. Okay, now let's find the number of negative solutions. So we're going to replace x with negative x and then simplify. Then count the sign changes of p of negative x. So replace every x with negative x. Now, when you have it to an odd exponent, it's going to keep the negative. If it's to an even exponent, you're going to lose a negative. So that gives us negative x cubed plus 6x squared minus 11x plus 6. Okay, so we don't start with the first term. We look at the second term because we want to know if it's different from the first term. Is the sign of the second term different from the sign of the first term? Yes. That's one. That's one variation. Now we look at the third term. Is it different from the second term? Yes. That's different also. How about the fourth term? Is it different? Yes. So there are 3 sign changes. So let me just kind of write this down. So from here to here, that's different. From here to here, that's different. From here to here, that's different. That's why we get 3. But we have to subtract by 2, so that's why it's 3 or 1. So we know in our answer that there's no positive solutions, and there could be 3 or 1 negative solutions. So at least we know we have 1 negative solution. So there could be 3, but there's at least 1. So what that does is when we're looking for numbers, we know if we're trying 1 and -1 and 2 and -2 and 3 and -3, don't bother with the positives. Just start with the negatives. So start with -1 and then -2, then -3. Okay, let's try another one. Again, don't solve it. P of x. How many sign changes are there? Is the second term different? Yeah, it is, right? So there's 1. How about this one? Is that different? Yeah. There's 2. How about this one? Different? Yeah, there's 3. So we got 3 variations in sign. So there's 3 or 1 positive solutions. Now let's do p of negative x. Replace x with negative x. And that gives us negative 3x cubed minus 2x squared minus x minus 5. Are there any variations in sign? Is the second term different from the first term? No. Third term different from the second term? No. Fourth term different from the third term? No. There are no variations in sign of p of negative x. Should be a negative there. I'll just write that in real quick. Sorry. So there are no variations of sign in p of negative x, so there's no negative solutions. So we know there's 3 or 1 positives, so we know we have at least 1 positive, and we don't have any negative solutions. So when you're trying your numbers, don't waste time with negative solutions, only try positive solutions. That's how this rule can help. It can kind of cut down our list or give you a better chance. If you know you have more positives than negatives, go for the positives. If you know you have more negatives than positives, or there's a better chance, go for the negatives. All right, let's do another one. So let's do p of x. Let's count the sign changes. How many sign changes do you see? I see 1 right here between positive 5x cubed to negative 7. That's 1. Oh, and then it goes back to positive. That's 2. And then it goes to negative. That's 3. So there's 3 or 1 positive solutions. Okay, now let's do p of negative x. Work it out. How many sign changes do you get? Well, I only see 1 right there. Then everything after that's negative. So that means there's 1 negative solution. So that's it. We have 3 or 1 positives and 1 negative. So if we're looking for a solution, I would probably try the positives, because we know we have at least 1 positive, maybe 3, maybe only 1. Again, those 2 could be complex. So what that means is you could have 3 positives and 1 negative. There's our 4 solutions. Or you could have 1 positive and 1 negative, and those 2 could be complex. How do we get complex? When you get a negative in the square root when you're using the quadratic formula. That gives us the I. Okay, here's one more. And then we'll get back to solving some equations. Again, we don't want to solve it. We just want to talk about what are the possibilities for the solutions. So let's count the sign changes. How many sign changes are there? Let's see, here's 1. That's 1 right there. Positive to negative. Next one is negative to positive. That's 2. Third one is positive to negative. That's 3. And then the next one's negative, so that's not a change. And the next one's negative, that's not a change. So that gives us 3. So that means 3 or 1. There are 3 variations in sign, therefore there are 3 or 1 positive solutions. Now we got to replace x with negative x. So do that and then simplify it. All right, let's count. How many do you see? It starts out negative, next one's negative, third one's negative, no changes, fourth one's negative. Ah, here we go. There's 1. Then it goes back to positives, that's 2. So I count 2 sign changes. Therefore, there are 2 or 0 negative solutions. So there's our answer. We have 3 or 1 positives. At least we know we have 1 positive solution. And we have 2 or 0 negative solutions. I know, it's not great, but it's what we got to work with. Okay, so let's go ahead and solve a problem, and let's see how some of this information can help make the process easier. Let's look at the solutions first. What kind of solutions are there? How many sign changes are there? Well, I see 1. Starts out positive, goes to negative, so I see there's 1. Then it goes back to positive, that's 2. Then it goes back to negative, that's 3. So there's 3 or 1 positives. How many are there altogether? There's 3. So if we do our p of negative x and we simplify it, notice what we get. They're all negatives. That means there's no sign variations. They're all the same sign going from term to term. So there's no negative solutions. So now we know when we're going to trial and error, again, hopefully you could use a calculator. But if you cannot use a calculator, then you got to do it all by hand. So we're not going to waste any time using any negative possibilities. We're only going to try positive numbers. So let's make a list. Our C is 1, 3, 5, and 15, and our D is 1. So C over D is just going to be the same numbers, 1, 3, 5, and 15. Now I put plus and minus, but again, don't worry about the minus. We're going to try 1 or 3 or 5 or 15. Okay, I ran out of room on this slide, so we're going to take it to the next slide, okay? Okay, so we're going to list our C over D, which is 1, 3, 5, and 15. And from Descartes' rule, we know not to waste any time with negative numbers. So we would probably start with 1, and you'll find that 1 doesn't work. So then we move on to positive 3, and that one does work. Okay, so that's x squared minus 4x plus 5. Does that factor? Let's see, 5 is 5 and 1, but they both have to be positive or both negative, and that's not going to give us a negative 4, so it does not factor. What does that mean? Right, quadratic formula. Okay, so A is 1, B is negative 4, C is 5. You should pause the video and work it out. All right, plug the numbers into the formula and simplify it. We get a negative in the radical. That means complex solutions, right? Square root of 4 is 2. And since it has an I, since it has a negative inside, then it'll be 2i. And then you can reduce it by 2. So that gives us an answer of 2 plus and minus I. So now we have our 3 answers. The answers are 3, 2 plus I, and 2 minus I. At the very beginning, we knew that we were going to have either 3 positive solutions or 1 positive solution. Well, as it turned out, we only got 1 positive solution. The other 2, they were sneaky, right? They were complex solutions. So Descartes' rule doesn't tell us if we're going to get complex, it says we could get complex. That's why we subtract by 2. So we knew it was either 3 positives or 1 positive. And it turned out we only got 1 positive. But no negatives. Complex are neither positive nor negative. They're just complex. All right, so here's a little note. This page is just going to be a couple notes. When it's the third degree polynomial, what did we do? We had to find one solution using synthetic division. Okay, the other two, they were either found by factoring or using the quadratic formula, or in some cases you can use the square root property if there's no x term. We had an example where we used the square root property. But that's the idea. We got to find one solution using synthetic division, and then we could solve the other two. Okay, now if we have a fourth degree polynomial, this is more complicated. We're still going to find one solution using synthetic division. But the result we get is still going to be a third degree polynomial. It's often called a depressed polynomial. We're going to use that depressed polynomial, and we're going to find one more solution using that third degree polynomial by, again, synthetic division. Then we'll get a new depressed polynomial of degree 2. I know this whole thing sounds a little depressing, right? Sorry. And then the last two can be found by factoring or the quadratic formula. So it's fourth degree, we got to find 2 by synthetic, and then the last 2 we could find by the quadratic formula or factoring. It gets worse. If it's a fifth degree polynomial, then you need to find 3 solutions using synthetic division, and then the last 2 by factoring or the quadratic formula. All right, so let's do a couple more examples and then we'll be done. Okay, 2 more to go. This one is a fourth degree polynomial. So let's list our C over D first. This is great because our D is 1, so anything over 1 is going to be the same number. So it's just the factors of 24. 1, 2, 3, 4, 6, 8, 12, and 24. And Descartes' rule, I'm not going to show it here, but you could show it on your own if you wanted to. There's 3 or 1 positives. You could see by looking at the sign changes. Let's see, 8x cubed is different from the first one, that's 1, and then 17 is different from the first one before, that's 2. And then the 24 is different from the 2x, that's 3. And then you do your p of negative x, and you'll get 1. All right, so I skipped some steps there. So Descartes' rule isn't great. It's telling us that we got 1 positive and 1 negative for sure, maybe 3 positive. Okay, let's find one of them using synthetic division, and I'm going to save you some time. I'm going to say let's start with negative 1. There's not much time. You probably would have started with 1 and then negative 1. So not too much time. So let's start with negative 1. And you see that you do get a remainder of 0. Okay, pause it. Make sure you can work that out. So now what we're going to do is that quotient that we got, 1, negative 9, 26, negative 24, we're going to use it again. And we're going to try to find a second solution. And I'm going to say, let's try positive 2. Now again, if you're able to use your calculator, you plug this into your calculator. The Casio will solve it. I have a video on how to use it. And so it's going to give you the 4 solutions. So you just look at your solutions on your calculator and say, okay, I'm going to try negative 1 by chance, but the calculator already told you. And then next you're going to try positive 2 by chance, and you'll get remainder of 0. So you don't have to do that trial and error. Unless your teacher is, really wants you to work and doesn't let you use a calculator, then you got to try all these different numbers. Okay, so now we got the 1x squared minus 7x plus 12. Does that factor? Yeah, it factors. X minus 3 times x minus 4, and then there's 2 answers there. So now let's list all answers. We have 3, 4, and don't forget the -1 and 2. All right, this is the last example. Just trying one more for practice. List your numbers. So there's our possibles using the rational root theorem. And again, if you use Descartes' rules, not great. 3 or 1 positive, so we know we got more positives, maybe. So let's start with c equals -1. I guess that's the one my calculator came up with first, so I said, let's try that one. But if you plug in your calculator and you get another one first, you could try that one first. It doesn't really matter. Okay, so now use that, the -1, -10, 31. So don't go back to the original polynomial. You use the depressed polynomial that we obtained after we found the first solution. So now we use the 1, -10, 31, -30, and then we're going to try 2 this time. And then that gives us x squared minus 8x plus 15. Again, I know I'm going through this really quickly. Make sure you pause it and go through each step. It takes a while. And then that factors. There's our 2 answers, 3 and 5, along with the first 2 that we found. -1, 2, 3, and 5. All right, that's it. I know it was a long lesson. There's a lot more to this. So just try to get through this one, and I'll see you here for the next video. Have a good day.